Alright, CNT140, Chapter 5, we're picking up on the section on which fiber. So here reminding you that most premise networks are using multi-mode fiber because of it's inexpensive, the distances usually are not that great inside of a building, so we can get by with using multi-mode. With long-haul systems using single mode, this would be maybe where you have a cross-campus connection. You know, I always think of like Penn State where you have, the campus is pretty widespread. So as you start connecting buildings, you might be using single mode to go from a main building over to the other side of campus and so forth. So inside of a building, most likely multi-mode. As I start connecting buildings, I might be moving over to single mode. Earlier, slower premise systems use LED light source with your OM1 fiber, but they found out LEDs were not usable above 250 meg. So as we moved into gigabit, faster versions need to be used. That's where they started using the VCSELs, vertical cavity surface emitting lasers, that offered enough of the bandwidth, if you will, with that fiber. So above gig, manufacturers started backing the older design of 5125, so they then adopted the OM2 fiber for higher bandwidth. And then again, further developments with that created the OM3 fiber. So now a lot of your 10 gig connections that are connecting closets will be OM3 fiber. And there is work on OM4 in the 40 to 100 gig range with, again, higher bandwidth connections. If you have an older premise cabling that have 62.5 fiber cabling, you have to look out for adding the 5125. Those two are not compatible with each other. The example I use here is think about hooking up a large garden hose to a small garden hose. When I do that, the water from the large garden hose is going to start squirting around the small garden hose. So these two are not compatible. I have to worry about interconnecting them. That's where color coding of the fiber and the connectors come into play, so you know what type of fiber you're dealing with inside. Because you can't look at the core and go, oh, it's that. I need the color code to help me. So the actual jacket color code gives you an idea of what you're dealing with, the type of fiber you're dealing with. Orange jacket down here, OM3 for, aqua jacket for OM3, purple jacket for OM4, and then lime green is pretty bright OM5. And then single mode is typically yellow. I can also look at the connector to know what kind of fiber I'm dealing with as well. If I look at the connector body, here I have a tan body, beige body, black, aqua, and those give me a clue as to what type of fiber I'm dealing with. All right. As I start dealing with fiber, there is different types of fiber cable that I might encounter. Copper cabling, 4 pairs. That's what I got. That's what I deal with. When I deal with fiber, I might have a variety of different types of fiber. The first one we start with, the common one we start with for connecting together two switches, if you will, is your simplex cable that is just 2 fibers. You have 2 fibers here, one send, one receive. The outer jacket has them connected together, and they end up calling it a zip cord. Here's what it looks like from the end, and here's what it looks like here. This is the kind of fiber we're going to terminate in the lab room. Just to give you an idea, that's the kind of fiber that is pretty common with your LAN backbone connections. A distribution cable now has a series of fibers that can be used to connect closets together. So with your distribution cable, as you see here, you might have 12 or 24 strands. So now I can run a large fiber count between buildings, and if I have 12 strands in there, that means I have 6 connections, because I need 2 fibers, send and receive. I would have 6 connections that I can make between those 2 closets. And that might be 2 or 3 switches that you're connecting together, because you might actually use two different unique connections on each switch. One is a main, one is a backup, or you might load balance those 2. So having a 12-strand fiber between buildings would give you 6 connections. That would be a distribution type fiber, and there's a color code to keep those straight. Actually, here's another one here as you take a look at. Okay. A breakout cable, this one I actually have even more fibers in, And here, as I see here, sometimes they are in bundles of. This bundle has a couple fibers in, this bundle has a couple fibers in, and so forth, giving you even a greater capability of connecting closets together. So as I look here, I have a bundle here that has a couple strands in, bundle here has a couple strands in, bundle here has a couple strands in, and so forth. So this can be used for, again, high fiber connections between two buildings, maybe across campus or something. Last but not least is the loose tube. This you would typically find outside, not so much in a building, but outside. And here, the actual fiber themselves, it's a little hard to see in this picture, but if I look here, I know this is not, and this is like a diagram, but as you see, there's actual tube and there's loose fibers in here. And those fibers usually don't even have any kind of jacket or buffer or anything on them. They are literally just loose fibers, but they do put a coating on the fiber that gives it a slight tinge of color, so you know it's the purple fiber or the blue one or whatever, and that'll allow you to know which fiber you're dealing with. A couple other that I'm throwing in that you want to at least be aware of, the book didn't mention. Here is a ribbon cable. As you look here, you have, I think there's 12 in this one. That again is taking up a small space, but if I have 12 fibers in there, I can have 6 unique connections. 6 unique connections. So sometimes you might see ribbon cable connecting entities together, closets together, whatever. You might also find air-blown fiber. Air-blown fiber, you actually install these, it's basically conduit with tubes in. You basically install the tubes, and then as you need fiber, you actually use air or vacuum, either suck the fiber through or blow the fiber through, and you can actually install that fiber when you need it. There's some unique applications about of this that I've read. Some athletic fields, think about like a football stadium, they actually put these tubes under the field to go from one side of the stadium to the other, and when needing another fiber connection, they literally just, kind of suck one through or blow the air through to push that fiber through and make a connection on each side of the stadium. I also read about this when the shuttle program was in effect. They put some air-blown fiber tubes up to the launch tower, and as they needed more fiber connections, they would just literally, kind of blow another fiber through or suck another fiber through to make a connection. If I look outside, I might find some aerial fiber cable. That, if I look at it, there's actually a steel cable in one half. That's the part that attaches to the telephone poles, if you will. And then attached to this is a sling, if you will. This outer jacket is all molded, but there's basically a sling down here holding the fibers. So the steel cable is attaching the poles and kind of making a hammock for the fibers underneath it, and the fibers go along for the ride underneath it. That could be between telephone poles. You might find fiber buried underground. If you do, you're going to have a fiber that usually has an armor layer here. And that's kind of like, think of it like a thick foil, like a tin can kind of thickness. And it's designed to resist the freezing and thawing of the ground. It's not going to resist a backhoe cutting through it, but it's there to kind of resist the breaking of the cable with the freezing and thawing of the ground, or shifting of the ground a little bit. And there is even undersea fiber optic cable too. And as you see here, there's layers and layers of armoring to protect it against the water pressure, because these cables are typically laying on the ocean floor. This map's a handful of years old, but it still gives you the idea. This is a map of all kinds of fiber optic links connecting continents, and those cables are literally laying on the ocean floor. Here's another one here showing you all the cables connecting continents. It's laying on the ocean floor. Here is some installers putting in. It shows you the size of it. And yes, they do even need to make it so that critters don't mess with it or chew on it and so forth. But that is laying on the ocean floor connecting continents. That would be an undersea fiber optic cable, which is another whole interesting discussion, if you will. All premise cables must be fire rated, your National Electrical Code Article 770. So as I deal with fiber cables, I'm going to run into that last letter again, general riser plenum, if you will. I'm going to run into the same kind of rating scale for fiber optic cables. OFNG, optical fiber non-conductive general purpose, that would be your patch cables. OFNR, optical fiber non-conductive R, for riser, connecting between closets. Closet on the first floor, closet on the second floor, you'd use a riser cable. And then OFNP for plenum, if I'm installing it above the ceilings, going down through the trays, down the hallways, connecting closets. And here's some samples. I found some riser cable, OFNR, And then down here, here's plenum, OFNP. And then this one has no, actually, no, this is an R right there as well. There's an R riser there as well. So if I look at that last letter again, that'll let me know whether it's plenum rated or not. Same as we dealt with in our twisted pair cabling. Color codes, we said before, the jacket of the cabling and the connectors, there's a color code standard out there to let you know. Here gives you, this is from the standard, is a look at the cabling, and I even put in a chart here for you again, kind of letting you see the jacket color code as well as the connector color code. That'll be a clue as to what fiber you're dealing with. Fiber connectors. Over the time, actually, all fibers need some kind of connection on. Eventually, I can pull fiber and then terminate, or I can actually have it terminated and pull it. That's something that can also be done. But my terminations can be done a couple different ways. We can actually fusion splice them together, or using a mechanical splice, I can splice them together. And the connectors themselves, I can actually, old school would be epoxy on, modern would be fuse the connector on, which would be the style we use later this semester. If you look at the history of early fiber connections used ST fiber connectors, and then along came manufacturers were like, hey, we can come up with something better. So the standards organization said, okay, as long as the signal moving through the connector is of this quality or better, so it did not have too much loss. Again, think about putting a connection on the end of a water hose. If you do a connection on the end of a water hose nice and tight, there's no water leakage. The same kind of idea with a fiber connector. If we have a good quality connector on there, light won't try to leak out. So the standards organization said, hey, as long as it meets this criteria or better, you can use different styles. Well, over time, different styles came along and they started creating different connector styles. So probably the first connector that most people use was the ST right here. It's kind of like a little twist lock on. A lot of places have moved over to SC, and some places even still use SC. Some places for a little while used MTRJ, and actually we had some switches early on that were MTRJ that we used, but most fiber connections now are using the LC connector. Now I have a bunch of different pictures here so you can help see them up close and personal and sort them out. ST here, SC here, MTRJ here. There's both fibers in one connector, and then LC here. This is what most connections are using now. Here's each one up, again close and personal. Here's the ST, straight tip, and then the port it would clip on, connect onto. And this just twist locked on. This was actually a very solid connection. The fiber line was really good. The light transfer from the fiber to the device was really good. So quality connection used for quite a while, but there was polarity issues. You could easily hook that up wrong, on the wrong side, if you will. Along came your SC, standard or square connector. Right here you have your send and your receives. This connector here, you can actually put a clip over both and help with the polarity issue, so you wouldn't get them backwards. Again, good fiber alignment, nice solid connection, nice solid connector. A lot of these were used for quite a while, and some connections might even still be using SC. Some switches moved over, or some connections moved over to MTRJ. Both fibers, send and receive, are in one connector into this port here, so you didn't have the polarity issue. It was nice and convenient, one cable click in, if you will, and you had a connection. But it was tough to get both fibers aligned to both ports in there. That was a lot to try to do. It's kind of like getting two bullseyes at once. Most modern connections now are using LC, loosened connector. These are nice, thin connection here, but you still have their individual cables. I put a clip around to make them act like they're together, but they're both individual cables and into a nice small space here. And this is typically what your fiber is going to go into, SFP, and then into your switch. We will be doing this later this semester, this kind of connection later this semester, and this is actually the type of fiber connector we'll be terminating. The next couple slides, I just show you some close-ups of the connector itself. There's the ceramic ferrule with the fiber inside. The teeny little dot inside is the actual fiber. And then I have one or two pictures showing all the parts of a connector. That way you can see all the pieces that go together. When we come back, we'll continue on.